Good afternoon, everyone. I'm very glad that you are here today with us. Welcome to our educational webinar on the electrical storage in Boost of Renewables. The Faculty of Economics and Business Administration organizes this event in partnership with the Austrian Energy Agency and also the UK-based technology intelligence company Exavat, and our media partner here in the country is also APSE, which is the Bulgarian Association for Energy Production, Storage and Trade. As you know, APSE organizes also a 2 days conference starting from tomorrow. It is about renewable energy sources and their deployment in the region. So this event was supposed to also gather students, our FEBA alumni, and also participants in the conference of APSE with some introduction to the techno-economics of electrical storage. I'm very proud to have also with me two of our guest lecturers, Simon Price, who is sitting right next to me, and Lukas Cvийб, who joined us online. I will tell a few words why this topic is important for the Faculty of Economics and Business Administration, and then I think that all of you received the agenda of this event, but I will give the floor first to Lucas and then to Simon, so that they will bring you first the Austrian perspective, some more basic concepts about electrical storage, which are the technologies currently on the market, and Simon will talk more about grid-based energy storage, and what can we expect from the markets, from the supply chain, what kind of cost paths can we expect, and what is the future perspective in the recent early year. So why this topic is important for the Faculty of Economics and Business Administration, in particular for my students in the Master Program of Energy Markets and Services, in particularly the course on renewable energy sources and biofuels. This is because in April 2002, the European Commission adopted the sixth version of the Bulgarian Recovery and Resilience Plan that allocates 6.3 billion euros to boost the Bulgarian economy in the next 4 years. So as you know, we have to deliver some major projects to deploy much more huge amount of renewable energies, and to ensure that they will be also integrated into the system. The deployment of electrical storage technologies takes a very significant part of the funding. Almost 18% of the national allocated grants are distributed among 3 major projects, which require to some extent adoption of new electric storage or new battery capacity. The main project is the large-scale battery areas project, part of the low-carbon economy pillar, which assumes that there will be grid-scale storage technologies. This kind of capacity will be based on the transmission system, and these projects also provoked our attention because in order to realize this project, Bulgaria needs first to deploy a new regulatory framework, and then to make sure that the costing which was assumed will be in line with the investment volume that will be realized to deliver the main milestone and the main targets. The timely realization of these investments, also the state capacity to utilize the funds, depends on some important factors, namely the maturity and also the cost efficiency of the available grid-scale electric storage technologies, the increasing supply chain constraints of critical materials, which will be also a topic we will discuss and address today, as well as on the regulatory schemes that should be introduced into the Bulgarian legislation to ensure socially just distribution of the project's costs and benefits. So that is why we wanted to see what is the experience of our partners, and I really hope this is like the first initiative to start working with them on this specific topic, but we'll continue also our collaboration in terms of developing of assessment tools or future events, knowledge and capacity exchange. So I will give the floor to Lukas Cvийб, who is an expert from the Austrian Energy Agency. Hello, Lucas. I hope you can hear me.
I'll jump shortly back because I think those three concepts of resilience, minimal costs, and sustainability are very important for the introduction of new technologies into our energy supply system. Resilience we're used to, and we need a reliable source of energy for most of our economic processes. Sustainability, of course, this is probably the main driving factor behind the whole topic of storage integration, is that we want to have a sustainable energy supply system that does not destroy our climate or our planet. And of course, we want to operate the system at minimal cost or very close to an economic optimum. So we do want the economically best options. When I said energy storage was always a part of the energy supply system, I want to provide three examples for that. First of all, probably most of you know pumped hydro storage, which are currently part of and very important part of the energy supply system, balancing demand and supply and providing additional services to the supply system. But also in the very recent past, like 100 years ago, we had huge energy storages. These are gas storages that are placed in the middle of Vienna. They were used to store gas for different purposes, mainly for lighting the city. But they were used and they were built to store energy. And now the system has changed. We do not have gas lighting anymore as a source of light in the city, and we do not need the storages anymore. But there has been a huge demand on gas storages all around cities in Europe. And lastly, this is more or less a symbolic picture of a pile of wood, which was historically throughout the ages an energy store that was used by humans to collect energy, store it, and have it available if they needed warmth or heat for cooking purposes. So energy storage itself is nothing new in the energy supply system, but as it is now, the integration of new forms of energy storage is the novelty. Why are we talking about energy storage in general? We have to decarbonize the energy system in order to protect the climate. And this decarbonization is largely based on PV generation, so photovoltaics and wind generation. And these sources are volatile by definition or by the kind, and this leads to an increased demand of flexibility in the system. And here we see a chart I took from a report that compares different studies assessing the necessity for storage demand within different shares of renewable generation. And on the x-axis, you see the share of demand that's met by variable renewable energy generation. And on the y-axis, you see the storage capacity compared to the peak demand. And you see that when we approach 100% renewable energy, we will need a certain degree of storage capacity. There is a huge volatility between the single studies, but there is a certain trend that with increasing renewable integration, this demand will increase and will form the optimal solution of the cost optimal configuration of the energy supply system throughout different countries. You see studies for Great Britain, you see studies for the United States and Germany. So this is more or less an important information in the long side. On the short end of time, where you see 20% renewable generation, 40%, you see the necessity for storage is relatively low, and even some studies suggest that there is no need for storage at all at those small levels, where you could use other measures of flexibility, such as grid extension or demand side management, to integrate those renewable energy generations into the net. And the last slide of my of the introduction would be the immense historical cost decrease we observed, especially by batteries, by lithium-ion batteries over the past decades, or especially years. And on the left side, you see a chart where the amount of produced batteries in megawatt hours. So the accumulated generation, worldwide generation, and on the y-axis you see the associated costs with it. And you see that with increasing produced capacity, the cost decreased dramatically. And this is what led us to a point where we are right now, where energy storage based on lithium-ion batteries is very cheap, and I suggest that now is on the border somehow to being profitable operated in the net, in the grid. On the right hand, you see a similar chart where the blue triangles represent observed prices for lithium-ion battery packs over the last 10 years. And you see a learning rate, so the black dotted line that indicates that the scientific community and the market is expecting a further decrease in prices based on economics of scale and additional learnings and new configurations of the batteries. What you also see is the demand on the second y-axis by different sectors. And you see that in blue and green and orange, the demand for transport is displayed. And only the small yellow area displays the expected demand from the energy storage side, and especially from the grid-scale energy storage is also less from that amount. So the main part of lithium-ion batteries is not going to be used in the as electricity storage. It's rather used for electricity storage for the means of transport and in battery electric vehicles. When we look at the energy supply system and the power supply system and the potential business cases for energy storage, we see that there is several potential business cases that storage could fulfill within the supply system, and these storages all work a little bit differently. So there's not only one purpose, like in transport, where we provide traction power, but there are many revenue streams that one could use to create a business case for an energy storage. So it's not that easy to say energy storage will be part or will be certain technologies will be part or won't be part of the energy supply system. I want to take a quick tour through the different supply and different revenue streams for a battery or an energy storage in general. So the most basic cases, which we will talk about a bit later also, is energy arbitrage, which means nothing less than buy energy at low prices and sell it at high prices and make some profit with that. This is mainly on the role level of energy traders. The second set of revenue streams would be on the level of system operators, which would be to provide services that help to guarantee the quality of supply. This would be primary response, secondary response, and tertiary response, that are services that help to stabilize the power supply and like voltage control and frequency control. The fifth application could be the peaker replacement, which means that you reduce the demand for power plants that are used to provide the capacity in only a limited amount of time during the maximum peak demand from the energy grid. Also, another revenue stream would be black start availability, so that you could provide services to start and restart the network without the need after an outage, or you provide seasonal storage for the seasonal fluctuations of the renewable generation. So there is increased PV generation in the summer. How do you save this energy for the winter times? Also, there are other revenue streams on the network operator level, especially deferral of investments and congestion management. And also there are some possible revenue streams for bill management, or in other words, for the consumers, that would take place most of the time behind the meter. So they self-optimizing the power consumption, self-optimizing the power generation, and providing power and the quality of power. When we look at storage technologies, there are several storage technologies. Actually, there are countless storage technologies. There are different chemistries of batteries. There countless methods of storing energy in mechanical ways, but the 10 most common storage technologies are pumped hydro storages, compressed air storages, where you compress air and then release the air if the energy is needed, and the energy from the decompression of the energy can be used to power a turbine, and you can generate energy from that. Flywheels, which is more or less rotary energy that can be used to store energy. We have several different types of batteries, and we also have, of course, hydrogen and supercapacitors, and all of them, or most of them, could be used, at least on a technical level, for different services within the energy supply system. And this is just a picture of the different storage types, and they're scattered along two axes. The x-axis is the storage capacity, so how much energy you can store, and typical durations of discharge, which means what amount of energy can you store in it, so in names of kilowatt hours, megawatt hours, gigawatt hours, and what are typical capacity to power ratios, so how long can you discharge energy from these storages. And you see there is a huge bandwidth of different storage technologies that could be used for different use cases. We have the big chemical storages like power to gas in form of hydrogen and methane up there for long-term storages, and we have the electrical storages in form of capacitors over there, and the batteries sit more or less in the middle. Yeah. On the next slide, I tried to paint a picture of the different applications and how they're typically used within an energy supply system. So on the y-axis, you have the duration of discharge. This means how long will the discharge usually be for the storage technology or for the service, for the application. And on the x-axis is the frequency, which means how often during a year, for example, will the service will be needed. And if you look, for example, up there, we have the seasonal storage, which has only limited times of discharge per year, but in order to shift the energy into the, for example, winter, it would have very long discharge rates. On the other hand, we have the quality control with primary response with very short discharge durations and high frequency of usage, which means these two are both storage technologies, but they do have completely different roles within the energy supply systems. And although theoretically both of these services could be provided by very similar kind of technologies, one would expect that there is a different optimum, economic optimum for storage that is designed to store energy in the summer and shift it to the winter, compared to a storage that tries to keep the frequency in a certain level and charges and discharges several times a day. Also, I highlighted the energy arbitrage type of revenue stream or application. because this is actually what we need in the first place for high level of renewable energy integration. And you see, we have somewhere between 100 and 1,000 charge cycles and about 4 hours of discharge duration, which we'll take a look at a little bit later. And I think the second presentation will also explain this a lot. This is the last diagram, which will focus on the classification of different storage types. This is, and also it's concluding the topic on the selection of optimal storage, or the selection of optimal storage, as we take a look at the costs, and we see on the y-axis the costs which one would need to pay for a certain amount of power, which means like kilowatts, and on the x-axis the costs of energy storage in capacity, in means of capacity, which are kilowatt hours. So on in this area here, you see all the storages which have a huge capacity and small related costs to capacity. For example, pumped hydro storages. They have the capacity costs are rather small because you have these huge amounts of water and stored at potential as potential energy, and rather high costs per kilowatt per power. Also, you would have the compressed air energy storage. You would have hydrogen storage systems here, or pumped thermal storage systems here. All these applications that have very low costs on the capacity side, so I mean the storage volume, and are suited for potentially long-term storages. All the storages on this side are suited for short-term storage, where you just need high power for a very short period of time, for example, for capacity reserves and voltage control, but you cannot store substantial amount of energy in there. Why is this so important for us, or for the topic of lithium-ion batteries? Because lithium-ion batteries sit here somewhere at the border. If you look for short-term energy storage, there are no, or the most battery systems are either more expensive in power or more expensive on energy related costs, which means that for these kinds of applications where you would need a very similar amount of power to energy ratio, lithium-ion batteries are currently one of the best options. Although there are there are several other technologies which would be better for other use cases because they have a better combination of between power and capacity in means of the costs. But in general, storage economics is not just the investment costs of the storage in euros per kilowatt hour. As I already mentioned, it's power related costs, it's also energy related costs. You have to account for the lifetime in years, as I mean the calendar lifetime, and also in the cycle life. So we do observe for some storage technologies there's a degradation or a maximum number of load cycles they can be used for. Also, there are different levels of discharge. You can't use the whole potential of all storage systems. For example, lead-acid batteries. You can use only approximately 50%. The same accounts for pumped hydro storages or most pumped hydro storage systems, where you cannot use all the water that is in the store. The next point is efficiency and self-discharge rate. Of course, the storage technologies do have different storage efficiencies. So what is the ratio of energy you have to use to charge the battery compared to the energy you get out of it when you discharge it? And this is especially for storage systems with a low efficiency rate very important. If the batteries get increasingly efficient, this factor, or the effect of this factor, reduces. And yeah, same accounts for discharge rates, especially if you plan on long-term storage, such as weekly storages or seasonal storages. Also, you have to account for the end-of-life costs, especially if you use storage systems that would become a burden at the end of the product life because of their components, because of their potential risks, because of the potential negative impact on the environment, and you have to account for them. And last thing, and probably one of the most important factors on the system, is also the energy market itself, with the potential to send price signals in order to make batteries operation profitable or not. And the same accounts for regulations. So if there are regulations in place that hinder battery storage, this is also something you would have to account for. For example, if certain value streams or revenue streams are simply not possible to do within the set of your regulations. And I wrote that storage economics is a rather complex topic, and during my work I stumbled across a paper where the authors tried to calculate the potentials over several revenue streams for battery storage systems in combination with renewable generation, and they analyzed the value streams and the financial streams. And this is just an example. This was their input table. So you have to keep a lot of factors into account if you want to optimize your storage system and want to find potential revenue streams for your energy storage system. Luckily, one could at least make them a little bit more comparable, which is the concept of levelized costs of electricity. And I think we're going to hear later in the second talk a little bit more about this concept. But one thing is very important when comparing energy storage technologies, is that they have different characteristics, and one would have to make a metric to compare them, and the levelized costs of energy storage are such a metric. And they consist of more or less the investment costs, the operation and maintenance costs, the end-of-life costs, so what would you have to pay in the end of life, the overall charging costs, so what price of energy would you have to pay, would you have to pay during the life of the battery divided by the energy, by the electricity discharged. So in the end effect, you get a levelized cost in euros per megawatt. What were your costs of the whole application of the system? And you could use this as a metric to compare different storage systems. And I think one thing that is really crucial here is that you have the electricity discharged in the nominator, and therefore this is one big leverage to reduce the cost of your storage system. So when you want to optimize your storage system, you want to increase the utilization rate. All the other factors are more or less predefined by the current economic situation. So you can optimize on the investment cost. You can optimize on the operation and maintenance cost. Of course, you can find some algorithms that decrease your charging costs, and you can find some good concepts for the end of the life of your battery system. But the one thing you could optimize during the design of your storage system is really the utilization rate and how often do you can you use the application. And this is one of the main takeaways, is that with increased full load hours, so with increased utilization rate of your storage system, either if it's a battery or a pumped hydro or an hydrogen storage, the costs dramatically reduce with the full load hours and the utilization rate of the systems. On the other hand, it's a complex question, and there's a lot of research done there, finding an optimum between the fixed cost and the degradation related cost. So as I already mentioned before shortly, that some storages, especially storages such as batteries, do degrade with utilization, but also utilization, or the utilization rate, is your biggest tool to optimize or to reduce your cost. So finding the optimum between those two costs is one thing you would want to have a very close look when you design battery systems or storage systems in general. And finally, the cannibalization. So the more you use storages, the more you reduce the potential value. This is for the first storage, this is for small storages and individual storages, this is neglectable, but with increasing storages, you do storage use, you do decrease the value of your storage. Of your storage activities. And to underline this, I want to present you a very simple example of energy arbitrage with a very simple approach, just to help you get the feeling of what are we talking about, what numbers are we talking about, and what to look at if you want to introduce an energy storage to the system. So here we plotted the development of the Bulgarian day-ahead prices, and this looks pretty much the same all over Europe right now. We had this time in 2019 with prices, we had some volatility, we saw some spikes from now and then. We had this we had this seasonal pattern with lower energy prices in the summertime and higher energy prices during the winter months, for example, here and here, which would be an incentive for seasonal storage. And of course, we saw last year this huge price increase for, because several reasons. I really don't want to talk about this right now. But what we also see is that the volatility during the day is greater actually than the volatility during the seasons, which makes a business case, or which is in favor, especially in combination with the utilization rate, for very short energy storage systems. So you see that during the day and during the weeks, the price fluctuations are much greater actually than during the seasons. Also, what we observed is that the high prices, in combination with the high prices, the volatility and the spreads of the prices also increased, and would form an additional incentive for the integration of storages. In the next slide, we prepared the mean hourly day-ahead prices for each year. So you see the prices for 2020, which was the first COVID year with slightly lower prices than 2019. We have this very slight diurnal pattern with the peak in the morning and the peak in the evening, and not too much potential for energy arbitrage. But if we look for, at the prices for 2021 and 2022, we see this huge increase, and also this huge increase in volatility between the early morning hours and the peak during the morning at 8 o'clock. We see a very strong reduction of the prices during the midday when PV comes out, and an increase for the evening hours. And this is also observable if we plot the energy prices as duration curves. So we sort them by price, and then we plot them, and in order to make them comparable also for year 22, we divided it by the number of the days. And what we could see is this overall increase in prices, but also this part where we have this very high prices driven by high gas prices and this scarcity in the market. We see that this potential here and here could be used for storage, for energy arbitrage. So sell this energy here and buy it here and make a profit. This is also just a little bit closer. We compared 2019 year and the 2021 year with the duration curves, and we see the maximal price of 2019 was 911 euros, and 2021 was 1,060 euros. They're on the same level, but the curves look completely different. So we have this very flat area here with small price peaks and very limited potential for real to buy prices at low levels and sell prices at high levels, which we compared in the year 21. There's much more potential right now in the market to sell energy at high prices and buy it at low prices. Or, I mean, the prices are higher, but they're relatively lower. And this axis I think there are deducted prices for storages with load patterns of 1 hour and 2 hour and 3 hours. So if a storage would charge for 1 hour a day and discharge for an hour a day, so it has buys the cheapest hour and sells the most expensive hour of the day, this would be the capacity necessary. And although those are extreme values, one can easily see that the business case in the current situation with high gas prices and potentially high CO2 prices would definitely make a better business case for storages with 1 hour, 2 hour, 3 hour discharge rates compared to the prices we observed before the energy crisis, which we're in right now. And this is also the last slide of this very simple example of energy storage. Is just a small model that for an energy storage with a capacity of 1 megawatt and a discharge of a power of 1 megawatt and a discharge capacity of a capacity of 1 megawatt hour and a power value of 1 megawatt. So this storage can store energy for 1 hour and then discharge energy for 1 hour. And if we want to follow this pattern, we charge it in the morning and discharge at 8 in the morning, and charge at 2 in the afternoon and discharge at 8 in the evening, and just do this every day. Following this simple algorithm, we can see that the average value of these charge cycles made per day for the morning circle and the evening circle really rose in the past years. And if this increases this effect, this will make a good business case for energy storage. And there are indications that this will and that this pattern will increase. Why will it increase? This price pattern is also known as the duck curve. It originates in California. They were the first to describe it. They have quite a huge PV generation capacity, and this capacity had an observable effect on the net load of the net and also on the prices. So the PV integration is highly correlated. So all the PV plants produce more or less at the same time. There's little potential for optimization, but this leads to a reduction of load during during high noon, and this consequently leads to a reduction of prices during these hours. So with increased PV integration, this effect will increase, and therefore the potential of the economic potential for energy storage will further increase. And the second development that highlights that there is a potential are the decreased capital costs and the decreased costs decreasing costs for energy storage and the prognosed decreased costs for energy storage systems. When we take a look at the costs, there is also a downside. Right now, we have about 60% of the material of the storage costs are as material costs, which means lithium and cobalt mainly, and only 35 to 40% costs that really could be optimized by economics of scale in the way that energy battery storage manufacturing price will decrease. And I think we will talk about this later, but the supply curve of lithium, and this is a rather old one, but there is also increasing. And this may lead also, on the other hand, to increasing battery prices, especially if one keeps in mind that the largest share of demand will come from battery electric vehicles that have a totally different cost component and demand component compared to flexibility within the net in the power supply grid. So there are other options for flexibility in the electrical grid, but there are limited other options in the transport sector compared to lithium batteries. Which leads me to the flexibility supply curve, which is quite a sound concept of how to decide or design flexibility measures in the large scale or in a greater context within the net. So you do have flexibility as you have a flexibility need based on the variable renewable integration, and this can be met via several different approaches. You could increase the forecasting. You could start to curtail renewable generation. So just simply do not use all the energy that is used by renewable generation, but additionally install additional generation to increase the share of renewables. You can of course integrate demand response on residential level, on commercial level, but mostly on industrial level. And so on. So there are a lot of flexibility measures, and generally and historically, energy storage was seen as one of the most expensive ways of introducing this flexibility into the grid. Although one can say that electrochemical storage is the cheapest or potentially the cheapest form of energy storage available in large scale for the flexibility demand. And lastly, I want to step one step back again and focus on the overall pictures. Today, if we talk about grid scale energy integration, we mostly here we see the solar power and wind power and hydropower into the electricity system, and we store the electricity for later electricity use. And this is where battery storage would be placed within this system. But there are other ways of providing this flexibility, especially if one looks at the greater system of the energy supply or of the energy need, where we would need also heat and transport energy or traction energy, and one can shift this electricity also between these sectors in form of power to heat or e-mobility, or in the form of power to X as some chemical storage between these sectors in order to to fulfill this flexibility demand on other levels than direct electricity storage. What are my key messages? The first one is energy storage was always part of the energy supply system. It will always be part of the energy supply system, and we will find some economic optimal solutions for energy storage systems within the systems. Especially battery storage is poised for rapid growth. As I mentioned, the cost decrease and also the increase in the effects that volatile renewable energy has on the price. Also, short-term storage, especially battery storage, is very compatible with complementable with PV storage, and the great seasonal storages such as H2 storages and methane storages for seasonal storages become especially important if you consider 100% clean energy scenarios where you won't have any reserve capacities in form of coal or gas peakers from from natural gas or coal. And finally, I didn't talk about this, but I think it's very important that we have to think about closing the lithium recycling loop in order to work with the huge amount of lithium that we will put into our system. Also, I added some sources. You can look them up later. Thank you.
Thank you, Lucas. Very extensive presentation. I'm very glad that you touch upon the different situation, particularly in Bulgaria, situation in the market, and the drivers of the prices. So it seems that storage will be really central part of our future energy systems, but if it's so needed and we see competitive demand or competitive uses. So the question is how prices will develop in the future. So I will ask this question our second guest lecturer, Simon Price from the UK-based technology consultancy Exavat. Hi, Simon.
Hello. Well, thanks, Maria, for introducing me. Thanks for inviting me to speak here today. This is the second talk I've given at the university, so I suspect that some of you in the audience may have heard me talking here a couple of years ago about solar PV, which was the core of what Exor did when it was founded, and we're still looking at PV. But we've expanded over the last 7 years into batteries and other areas as well. And I'll give you some background on that in a second. Thanks also to Lucas for a very helpful introduction. You've touched, Lucas, on quite a few of the areas that I was going to cover in my presentation. So I'll probably go a little bit lighter on a few slides and then spend more time in the areas where we don't overlap. But maybe I can reinforce a few of the messages that you talked about, which I definitely, or at least in most cases, I agree with. I have one point of disagreement which will become obvious as the presentation goes on. So, okay, that looks good. All right, so a little bit about Exor. My name is Simon Price. I'm the CEO. We were founded in 2015 in Sheffield in the UK. And I guess a good way to describe what we do is techno-economic analysis. So we have a research methodology that combines financial and business analysis with technology research, quite deep technology research, and forecast modelling that looks more like chemical engineering than anything else. And it's really the engineering that comes first with us, not the economics. And the result of that is that we're able to forecast the cost of materials, devices and systems in the industries we cover. And if we do our homework properly, make accurate predictions about where those industries are going. We focus on enabling decarbonisation through electrification. And that has 4 components, really. renewable electricity generation at one end, consumption of electricity at the other end, the electrification of everything is sometimes what it's called. Essentially, if you want to decarbonise it, you have to electrify it. And then in between, we have power conversion and transmission. That's where power electronics comes in, so getting the electricity from A to B. And then we have storage, so that the electricity can be delivered when it's needed. So if it's generated when it's not needed, you put it into storage, and then it's dispatchable on demand. And in terms of our customers, they kind of span the supply chain really, all across the supply chain, from mining companies all the way through downstream to large solar and storage developers who use our module cost tracking and forecasting, for example, to inform their negotiations with respect to long-term supply agreements. So we really do have kind of a whole system view. We look at these 4 pillars of electrification, and we look across the supply chains for all of those. So if we could go to the next slide, please. Maria. This is our UK. It's actually not the whole team, but some of our UK research team. We originally founded in Boston in the US, but we're now based solely in the UK, which makes a lot more sense for us as a business. If we can move on to the next slide. So in today's presentation, I'm going to look at 5 topics and kind of just a touch on the 6. So we're going to look at the key factors in techno-economic analysis. So what metrics matter when we're looking at stationary battery storage. We're going to look at some typical battery storage systems, very much touching on what Lucas has already talked about. We're going to look in more depth at the evolution of battery cost and how that relates to supply and demand for the critical raw material lithium. And then we'll have a look at what the implications are of that supply-demand imbalance on future battery costs and potentially on the levelized cost of storage. So what is techno-economical analysis? Well, from our perspective, it really comes down to 2 fundamental metrics. One is cost, and the other is performance. And part of our job is to try and figure out which technologies are likely to win over time in a given market. So if in storage, would it be lithium-ion batteries, would it be another kind of battery, would it be hydrogen, would it be flow batteries, etc. And generally, the technologies that win are the ones that deliver the highest performance at acceptable cost. And although it sounds kind of obvious, it's incredibly frequent that you'll hear analysts and consultants talk about the winning technology being the best technology, or the winning technology being the cheapest technology, and it's really not about being the best or the cheapest, it's about being the best at acceptable cost. And usually we combine these cost and performance metrics to create a figure of merit, or one or more figures of merit. And so some examples here are cost per kilowatt hour, which Lucas has talked about extensively. You could have cost per kilowatt. That's definitely something that would apply in the case of PV, where you're really selling power. At least at the module level, you're selling power and not energy. In a battery, you're usually selling energy, so cost per kilowatt hour is more important than cost per kilowatt. Cost per kilogram, so if you're looking at your raw materials supply chain, it's all about how much does each kilogram or each ton of material cost. And then you can combine those, so energy density, kilowatt hours per kilogram, gravimetric energy density, or volumetric energy density, kilowatt hours per litre, both of which matter a lot when you're talking about electric vehicles. You want a car that is more car than battery, ideally, or else it's no use. And then the ultimate metric, the one that really matters in every case, is the levelized cost. Lifetime cost divided by the lifetime energy generated or stored. So in PV, we would call that the LCOE, the levelized cost of energy. In batteries, we would call it LCOS, the levelized cost of storage. But in any case, it's important to define and figure out which metrics matter for a given use case. So I'll just take you on a quick detour into some work we've been doing over many years, since before Exelon was founded, for at least 10 years now, looking at the evolution of PV module manufacturing costs in terms of dollars per watt of cost, not price, but cost. But instead of looking just at the development over time, we've also looked at how that cost has changed in relation to the efficiency of those modules. And so what's presented here is, it is a time series, but the time series is just joining the dots. What you're really looking at is the module efficiency on the x-axis, so how much of the light energy is converted into electrical energy, or light power is converted into electrical power. And that on the y-axis is graphed against the manufacturing cost in dollars per watt. And you can see from that graphic that until about 2015, the cost of modules fell sharply. But over that time, the efficiency of those modules didn't increase by very much. So if you think of the cost per watt, the dollar per watt equation, the dollar per watt was coming down, but it was being driven by the dollars going down and not by the watts going up. And that's because the materials, the bulk materials that go to make modules, were driven from relatively small scale in the early 2000s to enormous scale by about 2010, and certainly by 2015. So we're talking about polysilicon that's used to make the solar wafers, we're talking about glass, encapsulant, backsheet, aluminium for the frames, and so on. The cost of those materials, as they scaled, fell dramatically. But in the early days of PV, or the early days of the mainstreaming of PV, performance was almost a secondary consideration. What we realised back in 2015 is that the dollar cost of modules could not continue to fall at the same rate as it had been doing. Most of those bulk material costs were reaching their lower limits. And so the only way to continue to decrease the cost per watt was to increase performance. In other words, get those expensive materials to work harder, to generate more energy. And that's what happened. So you can see here, there are two eras in PV. There's kind of pre-2015, which we call the cost reduction era, and there's post-2016, which we call the performance improvement era. And if you look in this graph, from about 2021 until now, the cost of modules has actually been going up, but that's a short-term supply-demand imbalance. But it's the kind of thing that you would expect to see in a product that has become reasonably mature. In other words, it starts to hit a point where its cost can't go down very much, but sometimes will go up depending on the volatility of the markets and the supply and demand of the materials that go to make that system. Either way, performance increases will continue to be critical in driving down the cost per watt. And we'll come back to this general thesis as we look at battery costs later. So the other thing that Lucas actually already noted is that the battery industry is already becoming dominated by EVs. And here I'm showing you some of our EV monitoring work, which informs our forecasts for the batteries and the semiconductors that go into those EVs. We're watching this space very closely, and it will have an impact on the cost of energy storage systems. Until recently, it's been beneficial. So the mainstreaming of electrification of transport has actually brought the cost of batteries down sharply, and energy storage systems have been able to benefit from that. But we're about to go into an age where the dominance of BEVs, battery electric vehicles, could be a problem for energy storage. So watching the EV market and considering how that changes is going to be very important to understanding the future of battery energy storage. So which metrics matter most in batteries? It's a lot more complicated to forecast the future of batteries than it is to forecast solar PV. And that's primarily because the metrics that matter in batteries are highly dependent on the application, on the use case. In EVs, we have to consider a wide range of factors. So perhaps the most important of these is the upfront cost of the vehicle. And that's driven largely by the cost of the batteries. So it's the battery capacity, it's the size of that pack, and it's the cost per unit of capacity, so the cost per kilowatt hour. And so if we want vehicles to get cheaper, we need either cheaper batteries. If we can't make them cheaper, we need to make them smaller. And right now, EV makers are not moving to an era of smaller batteries. They're moving to an era of larger batteries because of range anxiety. So the second big factor is vehicle range, and to increase the range of a vehicle, you need to increase the capacity of the battery, the size in kilowatt hours. And you also need to increase the fuel economy of that battery, so the number of kilometres you can drive per kilowatt hour. And that's a function to some extent of energy density. So if you can make a battery that's smaller or lighter, you have a car that's smaller and lighter, potentially, at least lighter, and that means it's likely to go further on a given amount of battery capacity. So you have these competing factors. And then the third important factor in EVs is the utility, is the usable space. You don't want your car to just be a battery on wheels. It needs to have space for people and bags and dogs and whatever else you want to put in a car. Right now, or at least the first generation, or the early generations of EVs, had very large packs and not much space inside them, but the new generation of EVs is being designed for purely electric applications, and they're now starting to create, manufacturers are now starting to create cars with more space inside them. Now all that matters in EVs, but in storage, arguably, apart from the cost of the battery, none of that matters. The only thing that really matters in battery storage, or the thing that matters most, is the cost. And it's not the cost, or not just the cost up front, it's not just the capital cost of those batteries, it's the levelized cost. So it's the cost of the battery, or the energy stored in that battery, over its lifetime. And that's where degradation and cycle life and those factors that Lucas talked about come in. And we'll study those now. So if we look at the LCOS, the levelized cost of storage, Lucas has touched on some of these, so I won't go into this too much. But the primary one is CapEx, the capital cost of the system. And that's a function of the rated power of the system, say 60 megawatts, and it's a function of the energy storage of the system, which itself is a function of the number of hours that you store for that rated power. So, for example, a 60 megawatt system with 2 hours of storage is 120 megawatt hours, and you're buying batteries in dollars per megawatt hour. So that's going to drive the economics of your system. Lucas also mentioned the round trip efficiency. A typical battery system is somewhere in the region of 80 to 85 to 90% efficient, which is pretty good. Now, some of those losses are coming from the battery itself, but many of those losses are coming from the electrical systems outside the battery, so the inverter and the cabling. So there's only so much you can do with the battery itself to increase the system efficiency. It's a whole system problem, and it requires you to look at things like the voltage that the system runs at and the kind of inverter that you might be using, which is another area that Exawatt focuses on. Now, if CapEx is very low, which is not in battery, but in certain other storage applications, if you have very low CapEx, you can afford to be more wasteful of that energy. So some long duration systems are arguably acceptable at less than 50%. So a system like a hydrogen system, it takes a lot of energy to electrolyze water into hydrogen, and it takes a lot of energy, or it wastes a lot of energy, recombining that hydrogen with oxygen in a fuel cell to generate electricity. So the round trip efficiency of the hydrogen system is way less than 50%. And it's still, in certain cases, acceptable. So the round trip efficiency is very much dependent on the duration of storage and how it interacts with the capex of that system. An expensive system, you need to make it efficient. And then degradation rate, that relates to cycle life. Lucas has already touched on that. In principle, for a PV system, the ideal battery is a battery that lasts as long or is warranted as long as the system, the solar system that it's attached to. If your system is warranted for 25 years, you want a battery ideally that lasts for 25 years without having to be repaired or replaced. And we're not there yet. At least we're not there for most battery types. O&M, operations and maintenance, is important, but it's small in the overall mix. And then finally, utilisation, which Lucas touched on, is critical because in a high capex system, high utilisation is low depreciation, and you need to minimise the depreciation cost to get superior economics. So here's an example. Lucas used some NREL modelling. I am too. They make available quite a lot of this data. So NREL based in the US, this looks at capital cost per kilowatt hour of rated storage capacity as the number of storage hours grows and the system gets larger. And as Lucas said, the cost per kilowatt per kilowatt hour goes down as the number of hours goes up. The reason for that is that the system power isn't changing, and many of the other costs in the system are correlated or related to the power of the system. So the inverter doesn't change. Most of the cabling and wiring doesn't change. Much of the system doesn't change as you make it larger. But the battery cost per kilowatt hour, of course, is constant across all ranges. So what happens is, as the system, the number of hours increases, the battery cost as a percentage of the system cost grows, but the overall system cost goes down. And so these numbers are a couple of years old, and they're for US installations, so we can't use them exactly in the Bulgarian context, but they give a reasonable indication of system costs. And you can see that in 2019, with a pack cost of $188 per kilowatt hour here, which was about right, batteries dominated the system cost, and they continue to do so. So I just wanted to take a quick look at what size of system makes the most sense for batteries. So if we're looking at a system to store PV, let's take the US, since we were looking at US data a second ago. This is an installation map of the US. It shows that the US average is about 4 hours of peak sun per day over the year, and in the southwest US in the desert it's closer to 6 hours, and with much less seasonal variation because you're much closer to the equator there. So if you were using a storage system just to back up PV, in the US generally an array of 4 to 6 hours would make sense, and in the southwest 6 hours or even more might make sense. Now what you'll see if you study applications for development of storage systems in California, for example, more than 90%, I actually think it's somewhere near 99% now, of solar systems being planned in California have 4 hours or more of storage. So storage, or solar plus storage, is becoming widespread in California and more broadly in the US. And 4 to 6 hours is the kind of the going rate. In Bulgaria, it would be a little bit different. So the Bulgarian average is about 3.5 hours of sun per day, and you'll all be more expert on that than I am. But clearly there's a lot more seasonal variation here. So a system that's set up to store PV only, PV energy only, might make more sense at a size of, let's say, 2 to 3 hours in Bulgaria. And in the UK, where I'm from, it's more like 1 to 2 hours because we don't have much sun. If we were looking at storing offshore wind power from the Black Sea, we might be able to move closer to 10 hours of storage, because the capacity factor for wind in the Black Sea is much higher, around 40%. In other words, 40% of the hours in the year are generating useful energy offshore from wind. And so think about that as a number of hours in the day on average. That's 9 to 10 hours per day. So 10 hours of storage over the year might be acceptable as long as there wasn't too much seasonal variation in your wind. And that's very much an area that I'm not an expert in, but I'd be interested to find out more about. Here we're looking at some NREL forecasts and an NREL analysis or a summary of published cost values for 4-hour storage systems in the US. And so alongside an NREL assessment of a high, medium and low case for the future cost, the future capital cost of that 4-hour system. And so you can see that in the high case, NREL, this is last year, believed that the long-term future battery cost or battery system cost would be flat. And in the low case, would go down from about $250, $300 in sort of the early 2020s, down below $100 per kilowatt hour by 2050. Now, I think in the long term, I would probably agree with that. The low case is plausible. But the problem is that everybody's been expecting, including us until recently, has been expecting the cost of batteries to fall steadily and quite significantly. And until a couple of years ago, we were expecting the cost of batteries to fall so quickly that by 2025, the cost of a battery electric vehicle would be about the same as the cost of a fossil-powered car. We no longer believe that's the case. We believe that battery costs could rise for the next few years at least, and that will have significant impacts on EVs and on the adoption of EVs, but it will also potentially have an impact on the adoption, or at least the planning and the capital utility, if you like, of energy storage deployments. So let's go back to our PV module analysis for a second and just recall that over time, the rate of cost reduction slowed, but the performance improvement continued. And more recently, the cost actually started to climb as the industry hit some short-term supply shortages. So if we go to the next slide and bring it back to batteries, Let's take a look at CATL. This is the world's largest battery maker. Enormously influential in EVs, something like 50% market share in China in batteries, and I think something like 25% globally. But also influential in battery storage systems because its primary focus is on a chemistry called lithium-ion phosphate, LFP, which has some properties that make it very suitable for storage and make it already widespread in storage. It's cheaper than the alternative technologies, chemistries that include nickel and cobalt. There's no nickel and cobalt in an LFP battery, which means it's less dependent on the volatility of nickel and cobalt prices. And it also has a very good cycle life. It cycles much better than what we call NMC, nickel, manganese, cobalt chemistries. And as we discussed earlier, the cycle life is very important in the overall levelized cost of storage. So a technology that has lower dollars, which LFP does, it's cheaper, and has longer cycle life, gives you a much better LCOS. Now, if you look here at the cost curve, you've got the declining cost and the declining price of those batteries up from 2015 to 2021. It looks an awful lot here like the battery cost reduction curve is also flattening. And it's possible, maybe probable, that we're moving out of the cost reduction era already in batteries and into the performance improvement era. And for many manufacturers, I mean, CATL is the biggest, it's the most efficient, it has good control of its supply chain. For many manufacturers that compete with CATL, their costs will have increased last year and will increase again and again in 2022 and beyond. And I'll show you why. So this is a very simple time series of lithium supply and demand. So the three blue lines represent the low, base and high cases for our forecasts for lithium demand, so in what we call LCE, lithium carbonate equivalent in million tons, from electric vehicles, okay? So by 2030, somewhere between 1.3 and 2.3 million tons will be required by the EV industry. Now, if you look at lithium supply, the red line here is a simple average. We've just taken we track the main mining companies in lithium, and there actually aren't many of them right now. There's a handful of mines in Western Australia mining rock, and a handful of miners or salt pond operators in South America who process and refine lithium brine. Now, we monitor those producers, and I've taken the average here of the forecasts that they see for lithium supply by the same unit, LCE, millions of tons, from now until 2030. And you can see that in 2030, the mean of their forecast is a little over 1.5 million tons, which is right around the same as our base case for lithium demand from EVs only. The problem is that there's no room in that forecast for the other markets that consume lithium. So you've got consumer electronics, phones, laptops, etc. And they already account for 100,000 tons, so 1.1 million tons, and that's going to grow over time, per year. Then you've got industrial applications, so things like greases, lubricants, ceramics. They account for about 0.1 million tons right now, and that is likely to remain reasonably steady. But then we've got grid storage, which we're here to talk about, and as Lucas showed in his presentation, I think it was NREL that he used, their forecast was that grid storage would not account for much demand. But let's just examine that for a second. Just think about solar PV, okay? We expect solar installations in 2030 to be somewhere close to 1 terawatt per year. So 1,000 gigawatts per year. That's up from about 250 gigawatts per year today. Now, if the average number of hours of storage across the global solar fleet was just 1 hour, and remember, the US is looking at 4 hours right now, and the US is a big market, but if the average number globally was just 1 hour, that would be 1 terawatt hour of battery storage, okay? That's about 800,000 tons of lithium requirement on top of this demand here. So you could, in that scenario, imagine that if the solar industry alone went for lithium with just 1 hour, that the total lithium demand might be somewhere closer to anywhere between, I don't know, 2.3 and 3.3 million tons per year, which is more than twice the expected supply from those mining companies. So the industry, whichever way you look at it, we're facing a serious shortage of lithium, and we have to look for alternatives. So this is already showing up in pricing. So this is a graphic that I took from a presentation a few weeks ago from AMG, one of the lithium producers. And you can see that from 2018 to 21, the price of lithium is actually going down. And many of these companies that were mining and refining lithium are actually finding it very hard to stay in business because they weren't making any profit. And then last year, the price started to climb, and it's still climbing. So every time I've done a presentation on the price of lithium in the last, I don't know, 6 months, I've had to change this graphic because the price keeps getting higher. So right now on this graphic, you're looking at somewhere between, I don't know, $70,000 to $75,000 per ton of lithium hydroxide and lithium carbonate. These are the two lithium precursor chemicals that are used to make batteries, or battery cathodes. Now, that's up from about, I don't know, $10,000 per ton or $10 per kilogram a couple of years ago. And most of the forecasts that you've seen, including Lucas's, were based on a $10 per kilogram cost. So this is going to be a major challenge for car makers, but also for battery storage developers. So let's have a quick look at the impact of this. And we do a lot of very detailed modelling at Excel on battery costs, and we look at not just the mining and refining of the lithium, but we look at the manufacturing of the cathode, the cell, the pack, and the system. But here I'm just going to focus on just the cost of the lithium in the battery, okay? In 2020, at $10 a kilogram for lithium carbonate equivalent, so lithium hydroxide or lithium carbonate, that was about $8 per kilowatt hour, something in that kind of range. It varies a bit by chemistry. It might be a little bit lower than that in an LFP battery, but it's broadly consistent. At a contract price of $25 per kilogram, that lithium would cost $20 per kilowatt hour. So it would effectively add $10 or $12 per kilowatt hour to the cost of the lithium in that pack. But remember, that lithium needs to be processed. It needs to be processed into cathode, then into a cell, then into a pack, then into a system. And at each stage, there's a margin being added on. So a $10 or $12 increase per kilowatt hour in the lithium cost might turn into a $20, $30, $40, $50 increase in the cost of that pack. And at a contract price of $50 per kilogram, you're going from $8 per kilowatt hour to $40 dollars per kilowatt hour just for the lithium. And again, there's margin stacking and processing going on in there. So you could well imagine that if we see long-term sustained prices back at that sort of $50 to $75 per kilogram level on the previous slide, you could imagine, I don't know, $50 to $100 going on the price per kilowatt hour going on top of the price of the recent price of the battery system. That is a major challenge, and it's likely to lead, well, it is already leading, battery storage developers and EV makers to look for alternatives. So what are those alternatives? Well, we're heading into this medium-term lithium shortage. It will probably resolve in the early 2030s, maybe sooner, because there's no shortage of lithium in the world, but there's a shortage of mining and refining capacity, and it takes time to build that scale. But in any case, battery storage systems are in a fight with battery vehicles for scarce lithium, and they could lose that fight. They could also win that fight. So if you determine that, or if the economics determine that the storage industry is more resilient to the increase in price of lithium than the vehicle industry, then battery storage systems win. But either way, it's a fight, and it's going to lead to increasing prices of lithium. So what does that mean? It means that the levelized cost of battery systems is unlikely to fall significantly in the next 5 years, and it could increase. So we need alternative solutions. And unfortunately, I don't have time in this presentation to get into those in detail, although I'm happy to talk about them in Q&A. But the two obvious ones to me would be, in fact there may be a couple of others which we can talk about, would be sodium-ion batteries. Essentially you're replacing the lithium ion with sodium. It's not quite as simple as that. You have to make some changes in the anode. You're still using a graphite anode, but you have to change the type of carbon that's used, and you have to make some changes in the cathode. But as far as we can tell, these changes aren't going to have crippling supply or resource constraints. So in principle, sodium is abundant, it's available in seawater and rock salt. Its chemistry is inherently safer. It operates at a lower voltage than lithium-ion chemistries. For the purposes of this discussion, that doesn't really matter except to say that it's safer. You can transport sodium-ion batteries fully discharged, which means you can transport them by sea safely. And some of the major manufacturers, including CATL, which we discussed earlier, and Reliance Industries in India, which just bought the UK developer of sodium-ion batteries, they're working on this technology already, and they're starting to make announcements about the deployment and the release of batteries based on this chemistry in the next 2 years. So it's coming, and in principle it should be cheaper. Now its energy density is lower than lithium-ion because the sodium-ion is larger, so essentially you can't pack your battery with as much energy, but it's not an issue for battery. It's an issue for vehicles, but it's not an issue for storage systems. Now, one unproven factor here is the cycle life, and that is a big determinant of the levelized cost, so we need to prove that. And so it's not a given that sodium-ion will win, but if sodium-ion does work, and it is lower cost and widely available, that helps a lot because it allows the lithium to be focused in markets where energy density matters, like battery vehicles, because you could argue that a battery storage system is kind of a waste of good lithium, really. It's a contentious point. And then another application or another alternative technology would be hydrogen and potentially flow batteries that generally work better in longer duration storage systems because they're an inefficient use of energy because they have lower round trip efficiencies. But if we get to a point where we have very widespread deployment of renewables, we quite quickly move into a world where people don't care so much about the cost of the energy, they care about the availability of it. And that's where hydrogen and flow batteries could extend their reach into areas that would today be considered the domain of the lithium-ion battery. And I think that's the end of the presentation. I've just left in a few email addresses here. For me, for Ed Rackley, who runs our battery storage, and for Aaron Wade, who works with Ed on our battery storage. And you can follow us all on LinkedIn. We'd be very interested in hearing from you. And I'll hand it back to you now, Maria, if you have any questions for me, but I know Lucas will be waiting as well. So thanks for your time.
Thank you very much, Simon. So now it's time for questions. So our participants can raise their hands, or the participants in the room if they have questions.
And if we don't, I'm going to have some questions. I've got some questions for Lucas.
Okay. First, the students have the priority, and Simon, you can ask Lucas.
Okay, so I think Lucas, I already mentioned it in the presentation, but I'm interested in your perspective now because I think perhaps you're closer to the policy side of this, you're closer to the downstream end of it maybe. And I'm much closer to the upstream, so I'm closer to the manufacturing and the supply chain, kind of what's practically possible. Your slide on the learning rate of battery prices, it's commonly used. Certainly, we were using that slide ourselves, and it comes from Bloomberg NEF originally, and they've been proven to be incredibly accurate forecasting the long-term price of PV modules. So the methodology that they use, I'm not sure which camera I'm looking at here, by the way, so I apologize for trying to figure out where you are. So that I agree with their methodology, and in the long term, it's accurate. It basically says as the cumulative installed capacity of a particular technology doubles, the cost of that technology or the price of the technology reduces by around 20%. And it's been found to be right. But my question is, my statement really is, in batteries, we have this supply chain problem now. That means we're going to move off that learning curve for, I don't know, 3 to 5, maybe even 10 years, unless we get
what you might call demand destruction through the emergence of alternative technologies. I just wondered if that had changed your thinking or what your response to that was.
Yeah, actually, I'm very happy that you focused on this topic and explained this so profound. We were talking about this and the whole supply chain issue very intensively, and we came strictly basically to the conclusion that we should use these learnings rates to determine the future costs, and that's like the most common idea. But in general, I do think, especially if you look at the supply chain and the potential and the growth in demand from electric vehicles, I think you definitely are right with what's concerning the mining capacities and the price development. I really think that the demand from electric vehicles would win this fight about lithium, especially because there are so many alternatives for battery electricity storages on a grid scale, like you said, the sodium-ion batteries or other technologies. So I would definitely agree with you on that.
Okay, so it's funny because when I saw your slide, I was prepared to in fact, in my early drafts of this presentation, I basically said it's a fight between storage and cars, and cars will win. And that the lithium industry definitely thinks that cars will win. But when I saw one of your slides, I can't remember which one it was, but I noted it as you were. It was looking at the cost per. I have a variant of this slide as well, but not in this presentation. But it's talking about the cost per kilowatt hour of each technology against, I think, the number of hours of duration. And it looks, you were saying that sort of batteries were in that kind of $300 to $400 per kilowatt hour range or something like that. And when I've been doing some LCMS modeling, again, I wish I'd had it in the presentation. I cut it out because I thought it was a bit too detailed. But if you look at the cost of lithium in the overall cost of a battery storage system, because the storage system has more stacked on top, it actually has less of an effect, or you could argue it has less of an effect on the overall cost of the battery. In other words, a lithium-ion battery pack in a car is something like $100, $120 per kilowatt hour right now, whereas a storage system is more like $250 or $300. So that corresponding increase in the cost of the lithium has more of an effect on the cost of the car battery pack than it would on the battery storage system, possibly because the storage system is less efficient right now. It hasn't been cost engineered down as much. You know, the car makers are brutal about how they cost, they demand cost reductions. So you're already seeing this in the car industry. You know, companies like Rivian haven't even launched a vehicle yet, and they've already put their prices up 10-20%. And Tesla's putting its prices up, BYD's putting its prices up. So I'm actually wondering if, arguably, if you look around in that space, in that curve that you have, even if the price of lithium went up and the cost of those packs went up, it still doesn't begin to encroach on another competing technology. It's still the best option, even if it's more expensive. I'm just wondering if you would agree with that.
I think, as you mentioned, there would be a race, and both prices would increase. And as you said in your last statement, the prices for electricity for vehicles already increased, but the demand for vehicles is so strong, and if they are not cost competitive, we would see, or we are going to see policy measures that incentivize electricity in vehicles, because all other options for vehicles are so there are not so many alternatives. Where you see in like the last slide, you do have so much possibilities to provide flexibility within the power system that it's very likely that you do not find large business cases for battery storage based on lithium. That's what I think. But I think in general the economics for other technologies such as sodium. And I'm very happy that you were talking about this, because we were discussing, shall we introduce the other technologies or the alternatives, or would it be too much to talk about those also?
I would have said, even a year ago, I would have said it's 5 years away, but it's coming fast, right?
Yeah.
Okay, I just see here is a question from Konstantin in the chat. Konstantin, do you want to intervene here in the conversation? But this is more.
No, it's in the office.
Okay. But I think this question is more related to PV installation, not really on battery storage. Maybe you'd like to know more about the return on investment of PV installation in combination with battery storage. I don't know if this would be possible to respond now, because there is a lack of information about the project parameters.
Right. I mean, you said it really.
Okay.
The issue for us is, for Excel, is we focus on what things cost, not what they're priced at. And the return on investment on the battery or the PV system is largely, there's a big factor in it, is the price that you're paying for your electricity. So if you're paying, if you're in the UK, you could install a system even at fairly small scale now, I don't know, €5 per kilowatt hour, let's say. But if I'm paying 10, that's a good deal. I could get quite a fast payback. But if I'm in a situation where I'm paying lower electricity costs, I'm not going to get my payback. So it's very much dependent on the spread between what its LCOE is, what its LCOS is, and what the price, the alternative price that you're paying.
Opportunity cost.
Yeah, basically. So it's I mean, I couldn't even begin to analyse that for a Bulgarian situation. I would imagine that the installation costs here will be higher. So there's a lot of inefficiency in the system, I'm guessing. I know that this is the case in the UK. So the UK is a highly efficient system for installing PV. In other words, what you pay for your system relative to the cost of the module is quite low, surprisingly low. Whereas in the US, it's incredibly inefficient, because you're always permitted and all these consultants and companies that all want their little piece. So the cost per watt of installed solar in the US is much higher than the cost per watt in the UK, even though the module costs are about the same. So there's all these factors that have to be taken into consideration. I know that from my experience in other industries, what you would call a distributor market like Bulgaria, where it's not a headquarters market, if you like, they're generally more expensive because it's third parties that are taking their little percentages all the way along. It's speculation.
Yeah, I think also another issue here is like operation of the system, so the balance. There are a lot of inefficiencies in terms of how you provide flexibility to the system, so that renewable energy producers usually have to cover this because of the lack of any other options. Okay, are there any questions from the room?
Yeah, I have one question. I don't know if.
Can you come closer to
Yeah.
us so that
Where's our mic?
maybe mic.
I'll just check.
So that the colleagues which are on
Here
the
or?
Where's the microphone here? Just here. Okay.
All right. Well, I think the question is in this case a bit more for Lucas, because it was mentioned in his presentation. I don't. Can you hear me well enough, or?
Lucas, can you hear?
No.
Okay, maybe I should come a bit closer.
Yeah.
Okay.
It's difficult logistics.
Yes, I wanted to ask. I was interested about this energy arbitrage that you mentioned, and if the cases that you showed, for instance, one of them being that there is such a volatilities during the day, so you have like a business case for during the day that you could store when prices are lower and sell when they're higher. If we already see this high volatility right now, why then isn't it? Why don't we see it's widely implied. For instance, within the retail market, this energy arbitrage. I mean, I don't see it that much in practice right now. If there is the opportunity to make money nowadays.
So actually, you have a lot of associated costs, and so in this very easy example, I neglected the cost. This was just the revenue you get from one cycle. But what I wanted to show is that with increasing prices and increasing volatility, there is a revenue potential. So to find and design an optimal system that would really to generate economic profit, you would have to look at the details and also include the whole system costs. You would have to include the grid costs, the insurance costs, etc., etc. And I don't think that this would be profitable, especially if you would consider that the price system as we have it right now is by far not stable at any. So I think if you would have asked somebody in 2019 if he would expect such prices or such volatility, they would say simply no. That's impossible. The system can't work on such prices and such gas prices, for example. But now we have these prices, and there is a huge uncertainty also in these prices in the long term.
Okay. Okay, thank you.
But maybe take a look at such an investment and see if it's profitable.
Sure. Yeah. Thanks. Thank you very much.
Okay, then we can further questions. Maybe I will raise a question about the policy takeaways that we can have from this conversation, because it seems that all kind of policies right now are pushing and giving incentives to constrain further on the supply chains of critical materials, because we need to fast find ways to encourage the transition in the energy sector, but also in the transport sector, and all these kind of fast movements, they don't actually catch up with all these market adaptation and adjustments that we also need to explore all other activities. Lucas, maybe you can share a bit about regulatory or policy options which are currently in question in Austria, and maybe Simon could also say a bit more about UK.
So actually in Austria we have the quite nice situation that we do have a huge potential for pumped hydro storage, which we can use, and there are right now about there's 1 gigawatt hour of storage under construction right now, and I think 2 gigawatt hours more are planned right now. So this would be a prime example for there are other storage technologies based on the availability of the geographic potential that would be cheaper than battery storage for renewable integration. On the other hand, those technologies do really have or could improve if you would reduce the grid fees for them. This is a main issue, especially if you want to increase the utilization rates and the profitable utilization rates. if you can remember these lines, the duration curves for prices, if you deduct the efficiency, the round trip efficiency of a storage, and then also add grid fees on that, you would reduce the potential for arbitrage, for energy arbitrage tremendously. So you could increase the value, the economic value of the storage if you exclude them, for example, from grid fees. That would be an example, if I got the question correct now.
Okay, I can't really speak to policy in the UK on storage too much. My understanding from talking to developers is that the fast frequency response kind of market has more or less been saturated in England, at least, in British Isles at least. It's still some capacity island for that. And that's very high value. So a lot of the investors were going after that market first because it's such high value relative to things like energy arbitrage. In terms of policy levers, this is definitely true of PV in the past, and it's true of EVs right now. We needed some policy levers to get incentives to get EVs going, but they've kind of got going now. So if you look at the UK, the biggest single incentive is the income tax credit. So if you're a business and you run your car through the company, you essentially, if you're in a higher tax bracket, you're paying 30-40% tax, you get a 30-40% discount on the car. So that's what it works out as. And so that's meant that people who would otherwise be buying out a BMW or whatever, they're going for a Nissan Leaf or a Hyundai Kona or something, because it's just, it makes that car relatively affordable. And once you've got it, it's much cheaper to run and it's much better to drive and so on and to use. So that's led to this incredible quick, that tax credit came in about 2 years ago, and that's just led to this boom in the UK. We're at a point now where, if we're not careful, that's going to just take up all the demand for no real benefit. It decarbonises the UK economy a bit and it encourages EV production. But what we really need is to encourage upstream mining and refining, not downstream purchasing, because any incentive just goes straight or pass straight upstream to those miners. We need to get those mining capacity, that capacity and refining capacity growing, not feed money into the funnel at the other end. Does that make sense?
Yeah.
Okay.
Good. Thank you very much for your inspiring participation. Thank you also to all our participants, both online and here in the room. And see you soon. Probably again talking about renewable energy integration and storage deployment. Lucas, thanks again, and have a nice day.
Thank you for having me.
Bye.
Thank you for having me. Bye.